In this PowerPoint, we're going to be talking about gases and some of the theoretical gas laws. Now, why do we need to know this stuff as HVAC technicians? Because the entire refrigeration system is based upon gases, gas temperatures, and gas pressures. There is a theoretical component to this that technicians should be familiar with. Do I expect you to memorize all of this? No, but this is some background information as we continue to talk about the refrigeration cycle, design, and what can go wrong with the refrigeration cycle. So the objectives for this chapter, which goes along with chapter 5 of the Modern Refrigeration book, 20th edition, if you have that, describe the effects on gas pressures and temperatures when volume is increased or decreased. Describe Pascal's law and provide examples of it in the HVAC industry. We want to be able to illustrate the effect of pressure and heat on the three states of matter. Now remember, the three states of matter: solid, liquid, and gas. We want to differentiate between gauge pressure and absolute pressure. We want to understand how the concepts of Boyle's law, Charles' law, Gay-Lussac law, and the combined gas laws explain the behavior of the refrigerant in the operation of a mechanical refrigeration system. We want to describe Dalton's law and explain how it can be applied to HVAC work. We want to explain the significance of saturated vapors in a refrigeration system. And you want to describe the processes of air exchange, pressure change, and state change to provide a cooling effect. So, just a reminder, volume is the physical space occupied by a substance. It can be measured in liquids and solids. It increases when a substance is heated and decreases when a substance cools. Now, gas is a little bit different. If you heat the gas in a fixed container, the volume will increase until the container is filled. Additional heat energy increases pressure and temperature. Pressure is a force per unit of area. In the US, it's pounds per square inch, PSI. Standard system, which is international, is pascals or kilopascals. All substances exert pressure on surfaces supporting or containing them. Okay, in other words, if I put something on a desk, it's exerting pressure. If I increase the air pressure inside a house, it's creating pressure on the outside walls. If I have water in a pipe and increase the pressure, it's putting pressure on all walls of that pipe. So pressure exists within any substance that has a higher pressure or lower pressure than the surrounding area. So there's several formulas for calculating pressure. The basic formula is P equals F over A, where pressure equals the force divided by the area. Okay, so if we have the first example, I have 250 pounds of pressure, of force, 250 pound of weight coming down on the wall or on the floor over a 10 square inch area. We take the 250 divided by the area. I now have 25 psi. That's pounds per square inch. If the force increases, the pressure increases. So now I have a force of 500 pounds on the 10-inch square area. It's now 50 psi. And if the area increases, the pressure decreases. So going back to the first example, it was a 10 square inch area. Now if I move it to 25 square inch area, I have 25 or 250 pounds of force divided by 25 square inches. My pressure decreases to 10 psi. Pascal's law basically says that force is applied evenly to all directions, okay? So I have 60 psi of pressure on the gas inside. I have 60 psi on all walls of whatever vessel is holding the gas. Pressure doesn't magically drop from one place to another. There is a relationship of pressure to volume and heat. If as heat is added to any substance, it can increase in volume, it can increase in temperature, and it can increase in pressure. If the volume of gas is decreased, it may increase in pressure and it can increase in temperature. In other words, if I have a cylinder full of a gas, and if I decrease the size of that cylinder, okay, I'm going to increase the pressure of the gas within that cylinder, and I'm going to increase its temperatures. That's called heat of compression. Adiabatic compression is the compressing of gas without gaining heat from or losing heat to its surroundings. We also have an effect on pressure of the physical state of the substance. Pressure affects the temperature at which a substance changes its physical state. Higher pressure requires higher temperature. Lower pressure requires lower temperature. So, for example, a low pressure in the evaporator allows evaporation of refrigerant at a low temperature. This is called critical temperature and critical pressure. So if we take a look at the pressure at boiling of water, okay, and the temperature at atmospheric pressure, which is my dotted line, okay, let's get my mouse pointer over here. I have two dotted lines come together. This is the boiling point of water at atmospheric pressure, 212 degrees or 100 degrees Celsius, okay, atmospheric pressure. If I increase the pressure going to my right, okay, I increase the pressure, my boiling point of water goes up significantly. If I decrease the pressure, my boiling point of water comes down. So if I have a 0 psi, that's absolute, okay, if I come down as close to 0, I can actually boil water at room temperature. Now, if we take and substitute out refrigerants for this, we can see where my boiling points and points will drop and raise based on the pressure of my refrigerant system. So we have some different pressure scales we have to talk about. Gauge pressure is always PSIG. Okay, 0 PSIG equals atmospheric pressure. 0 PSIG equals 14.7 PSIA. That's a number you have to remember. 14.7 PSIA, that's absolute pressure, is 0 PSIG. Pressure above atmospheric pressure registers on gauges. Absolute pressure scale, which is PSIA, 0 PSIA equals the pressure that cannot be further reduced. It's a perfect vacuum. Any pressure below atmospheric pressure is a partial vacuum. So we have different units for pressure measurement. We have pounds per square inch, PSI. We have inches of mercury, Hg. We have feet or inches of water column. We have torrs. We have bars. We have atmospheres, and we have kilopascals. The inches of mercury was the primary form of vacuum measurement, okay? The more vacuum you pull, the mercury will drop down, okay? So atmospheric pressure pushes the mercury in the bowl down and keeps the mercury here in the container, okay? This up here is a vacuum. If I decrease the pressure here that's pushing down on it, this liquid level will come up and the mercury will drop in the tube. Therefore, we can measure based on the inches of mercury in the tube. Now, of course, we really don't want to use mercury anymore because it is a hazardous material. The other device that's used and is still used is the water manometer. Okay, We use this for duct pressure measurements and any low pressure, low vacuum air measurements, okay? We take a tube, it's called a U-tube, we fill it with water. And when at atmospheric pressure, or just holding it in your hand, the water level is equal. When we put it in a duct pressure, we can actually measure how much that water pulls back. Again, that's inches of water pressure. Compound gauges provide us with both PSI and vacuum. Okay, a compound gauge, it measures both a positive pressure or a vacuum. It often includes saturated refrigerant temperatures that correspond to the pressure reading. It's used on the low side of the system. Okay, and you don't anymore use these when you put a system into a vacuum. We use a different set of gauges for that, or different gauge. Now, Boyle's law says the volume of a gas varies inversely to the pressure, provided the temperature of the gas remains constant. Charles' law says the volume of a gas varies directly to its absolute temperature, provided the pressure of the gas remains constant. So here we're talking about the volume of the gas is inverse to the pressure. In other words, if I keep a temperature of a gas constant and start off with a small container, and then I have it pressurized to 10 psi, and if then I put the same gas into a larger container, the pressure is going to drop, as long as the temperature remains constant. Charles' law says the volume of the gas varies directly to its absolute temperature, providing the pressure remains constant. Gay-Lussac's law says the absolute pressure of a gas varies directly with its absolute temperature, provided the volume of the gas remains constant. Now, this is extremely important for the temperature-pressure relationship. If I take a refrigerant cylinder and if I throw it on a freezer for a couple hours and take a pressure reading, once it gets really cold, I'm going to have a certain low pressure. If I take it out of the freezer and put it in the sunshine, okay, and let it warm up, the pressure is going to go up, but the volume of the gas has not changed. It's still in the same container. There's a temperature-pressure relationship. This is what happens inside a refrigeration system. The volume of my gas is not changing. Okay, there's only so much gas that I've put into this refrigeration system. Might be 10 pounds, might be 3 pounds, might be half a pound. Okay, there's only so much gas I've put into it. But the temperature and the pressure changes. On the high side of the system, I have high pressure, high temperature. On the low side of the system, I have low pressure and low temperature. That's the basis of the refrigeration cycle. So we have what's called a combined gas law. It combines the principles of Boyle's law, Charles' law, and Gay-Lussac's law. The ratio among the pressure, volume, and temperature of gas remains constant. Okay? Again, there's a temperature, pressure, and volume relationship. Okay? It can be rearranged to solve for temperature, pressure, or volume as long as you have the other two numbers. Avogadro's law and the ideal gas law. Avogadro's law equals equal volumes of two different gases at equal pressures and temperatures contain equal number of molecules regardless of the mass of the gas. The principle of this law and the combined gas laws produce the ideal gas law. The ideal gas law provides a formula for calculating the pressure, temperature, or volume for a known quantity of gas. This is primarily used by engineers rather than technicians, but this honestly does appear on some certification and licensing exams. Ideal gas law provides a formula for calculating the pressure, temperature, or volume for a known quantity of gas. Okay, the formula to calculate pressure, temperature, or volume is the ideal gas law. It's the basis for many charts and tables that you use as a refrigeration technician. Dalton's law says in a mixture of gases, each gas acts as if it were occupying that space alone. The total pressure of a confined mixture of gases equals to the sum of the pressure of each gas. Okay, so if you have gas 1 and gas 2 equals gas 3. Now this is used with pressure temperature charts and pressure measurements to determine if there's non-condensables in the system. Let me throw an example out here. If you have an R22 system with a pressure of 60 psi, okay, it means that your evaporator temperature should be around 36, 40 degrees, someplace right in there. If your evaporator temperature is much higher, it means there's another gas in the system. Or if you have a standing system that you've shut down, okay, and let's sit for a while so all the pressures are equalized, okay, you turn it back on and all of a sudden your high side system side shoots up to 400 psi, but you know what refrigerant you have, you know what the temperature is of the liquid line. You can find out if there's a non-condensable in that system because it's two different gases. And one gas is going to look to a different temperature-pressure relationship than another gas. Actual refrigerant pressures equals actual measured pressure. If I have an actual refrigerant pressure less than the measured pressure, I might have a system that contains both refrigerant and air. It's just what I talked about on the prior slide. Saturated vapor is a term that's pretty important. It's the condition of balanced on an enclosed quantity of fluid. When a vapor is saturated, often some of the substance is already present in a liquid form. It's usually found where the change of state occurs, such as evaporator and condenser. By change of state, we mean changing from a liquid to a gas or a gas to a liquid. Saturated vapor is where all of the substance that can be vaporized has been vaporized. If heat is added or the pressure is lower, more liquid will vaporize. If heat is removed or pressure is increased, more vapor will condense. It's that point of condensation or vaporization. The basic process that provides the cooling effect is air exchange. Heat is transferred from warm air to a cooler surface. Heat will always go from a warm to a cool location. We do pressure changes. Decreasing pressure on a gas can cause it to expand and its temperature to drop. As it comes out of the metering device, we decrease the pressure, we cause the gas to expand, and its temperature will drop. State change, a solid changing to a liquid or a liquid changing to a gas, absorbs heat from the surrounding area. Let me repeat that. A solid changing to a liquid or a liquid changing to a gas absorbs heat from the surrounding area. So in a refrigeration system, we take the high pressure, high temperature gas that's coming out of the compressor. We put it into the condenser. That temperature is high and the boiling point is higher than the surrounding air. Okay, so we actually reject heat to the surrounding air because of the high pressure. Our boiling point is high, so we condense that refrigerant to a liquid. We further cool that liquid by blowing air across the fins, and we send it on its way to the liquid line to the metering device. In the metering device, we drop the pressure of that gas, as we push it into the evaporator. Dropping the pressure significantly lowers the boiling point. Anytime we boil a liquid to a gas, we absorb heat from the surrounding area. So as that liquid is boiling off in the evaporator, we are absorbing heat. Anytime you absorb heat, it makes the surrounding area colder. We take that gas, we pull it back through the compressor, we compress it into a high pressure, high temperature gas by heat of the compression cycle and just heat of compression, and also we absorb some heat from the motors in the compressor, and we start its whole cycle again. But the entire mechanical refrigeration is based on these three items: air exchange, pressure change, and state change.